Hello everyone, today we are gonna talk about a very important topic, that is effusion. First we'll write the definition for it. So effusion is the process by which gas molecules escape through a very tiny hole. Effusion is the process by which gas molecules escape through a very tiny hole in a container without any significant collision with other molecules. So this is the definition for effusion. We'll draw a container where we have helium and neon gases and there's a tiny hole through which they escape without significant collision. It's called effusion. Now we'll discuss about a very important law, that is Graham's law of effusion. So to understand it, we'll write that under similar conditions of pressure and temperature, this law is valid only under certain similar conditions of pressure and temperature. We'll write that the rate of effusion of gas, that is R, is inversely proportional. The rate of effusion of a gas, which is R, is inversely proportional to the square root of its density, right? So we'll write that rate of effusion is inversely proportional to square root of density of this gas. So this is valid only when pressure and temperature are kept constant or they remain same. So we can use R to represent rate of effusion and D for density of gas. We know that pressure is dRT by M, where M is molar mass, right? So how we got this equation, I will explain in a moment. So we can write that R is inversely proportional to square root of molar mass. We know that PV is equal to nRT. N is given mass divided by molar mass, which is mass of gas divided by molar mass of gas. So this is the ideal gas equation. We can write PV is equal to small m divided by capital M into RT. So small m by V can simply be written as density. So from here we get P is equal to dRT by M. So we can write that when there are two gases in container, let's say there are two gases, gas 1 and gas 2, the rate of effusion of first gas is R1, rate of effusion of second gas is R2. We can write R1 by R2 is relative rate of effusion, right? So rate of effusion of first gas with respect to second gas, because we have written as R1 by R2. If it was R2 by R1, then rate of effusion of first gas will be replaced by rate of effusion of second gas with respect to first gas. So R is inversely proportional to square root of density, which is inversely proportional to square root of molar mass. We can write R1 by R2 is equal to under root of D2 by D1 or square root of M2 by M1, considering pressure and temperature remain constant. We can write rate of effusion R in other ways. We can describe it as R is basically moles of gas effused out divided by time taken, or we can also write it as that volume of gas effused out divided by time taken. Other way we can write it as is distance traveled by gas effused out divided by time taken. Another way can be decrease in pressure of gas effused out divided by time taken. So these are some ways we can define. So R is basically amount of gas leaving divided by time taken, that is rate of effusion. Amount can be anything, moles, volume, distance covered in tube, or pressure drop. So these are some ways through which we can define effusion. Depending upon a problem, we can use any of these definitions, right? So the most important definition remains the same, that rate is inversely proportional to square root of density, which is inversely proportional to square root of molar mass. So let's solve a problem. Here we have a 24 centimeter long container and there are two gases, gas A and gas B, with molar mass 10 and 40 gram per mole respectively. And at the center, let's say they meet, and x is the distance from left end where they meet. We have to find this distance x. So we can write this equation or formula which we derived earlier, that R1 by R2 is equal to under root of M2 by M1. R is the distance traveled by gas divided by time taken, right? We discussed about it earlier. So here we can write R1 is equal to x divided by time taken t. For second gas we can write R2 is equal to, this is gas 2, this is gas 1, R2 is equal to 24 minus x divided by time taken t. So we know the formula R1 by R2 is equal to square root of M2 by M1. We'll put this value over there. So under root of, what is the molar mass of second gas? That is 40. Molar mass of first gas, that is 10 gram per mole. So we'll get 2. X divided by 24 minus x is 2. So solving it further, we'll get x is equal to 48 minus 2x. X will come out to be 16 centimeter. This will be our answer where these gases will meet. So distance that gas A has moved. So now we'll solve another problem. 1.6 gram of CH4 effuses through a small pinhole in 60 seconds. Find weight of HE gas effused out in 30 seconds under similar conditions. This is important point to note here, that pressure and temperature remain same here. We have two gases, CH4 and helium. 1.6 gram of CH4 weight is given. Molar mass for this gas is 16 gram per mole. You can calculate very easily. Time given is 60 seconds. For helium weight, we have to calculate how much it is effused out. Molar mass we know 4 gram per mole. Time given here is 30 seconds. So I'll ask you to pause this video for a moment and solve yourself. We know that rate of effusion is mole of gas effused out divided by time taken, right? So we can write R is N by T, moles divided by time taken. R for CH4 can be written as moles of CH4 divided by time taken by CH4. Here it is 1.6 divided by 16 divided by 60. Simple calculation, it will come out to be 1 by 600. Similarly for helium, we'll solve it. So we'll get W, which we have to calculate, divided by 4 divided by time taken. Here is 30 seconds. So it will come out to be W divided by 120. And we know that R1 by R2 is under root of M2 by M1. So 1 is CH4, 2 is helium. And we can solve this very easily. So we'll put these values, that is R of CH4 and R of HE. We got these values. 1 divided by 600 divided by W divided by 120 should be equal to under root of 4 divided by 16, which will come out to be 1 by 2. So 120 divided by 600 W should be 1 by 2. So 240 should be 24 should be 60 times W. We can further solve it and get the value of W. It will come out to be 0.4 grams, right? So this will be our answer, the weight of HE gas effused out in 30 seconds.